I'll be talking about generative models of brain network wiring. And so in this work, we try to specify formal models that outline or define different wiring rules that we might think might be important in shaping the architecture of the connectome. And then we grow those models computationally and we compare them to our data. And if there's a decent fit between the model and data, we think, well, the rules in our model tells us something important about how the connectome has come to be. Before we get started, I'll just point out that a lot of the work and ideas I'll be talking about today and some of the fancy animated slides were developed by Stuart Oldham, who did this work as part of his PhD. And a lot of the work was just published in this paper last week. And there's a link to the preprint there for anyone who's interested. But if you do miss anything, please feel free to email me or reach out on Twitter, and happy to follow up. So I'm going to focus on three different aspects. So I'll begin with a bit of a background as to why we might want to use generative models. Then I'll talk about how we go about specifying these models and fitting them to data. And then I'll talk about some considerations that have come up in our own work in this space that I think are useful to keep in mind as we try to develop the field forward. So I'll begin with a bit of a background introduction to generative network models. And again, this is kind of in the spirit of this educational workshop. So trying to be a little bit more didactic, and hopefully I'll be able to give you not only a background, but a bit of a feel for how this sort of work is done. Now, this is the brain connectivity workshop, so I'm presuming that most people are going to be familiar with the concept of a connectome, but just in case, just to make sure we're all on the same page, the connectome is a very fundamental concept in this area. It was first defined by Olaf Sporns, Giulio Tononi, and Ralph Cotter in 2005 as a comprehensive structural description of the network of elements and connections forming the human brain. So there's two critical ingredients of this definition. So one is it's a structural description. So we're talking about anatomical or physical connections between brain regions. And the other is that it's a network description. And so really, if you think about it, we can find evidence of networks at lots of different resolution scales in the brain. We can map networks of individual neurons and synapses at microscale, networks of populations of neurons linked by axonal fibers at the mesoscale, and also networks of macroscopic brain regions linked by white matter bundles at the scales that we typically consider when we're talking about human brains. And really most of what I'll talk about today is concerned with trying to model these macro scale human brain networks. There's a pretty well-established pipeline for generating connectomes using brain imaging data. The basic idea is that we parcellate the brain into different regions or areas. These act as our network nodes, and then we map some aspect of functional or structural connectivity between every pair of nodes. We then represent that in the form of a adjacency matrix or connectivity matrix. So here each row and column represents a different region, and each element tells us about the type and strength of connectivity between areas. And equivalently, we can get a graph-based representation of the network from this matrix. So the regions are represented as nodes, and we draw an edge between them if they're connected in some way. We can then go on to do two broad classes of analyses. One is focused on just connectivity, so looking at variations in the strength and connectivity between nodes. And the other is focused on the topology of the network. So technically, the topology of the network refers to any property of the network that does not change under some continuous deformation. So you can imagine if we stretched or rotated the network, the basic pattern of pairwise connectivity between two nodes would be the same. So this defines the topology, the actual underlying way in which connections are organized in the brain. And we can use graph theory to derive lots of different measures that allow us to quantify different topological properties of brain networks. And there's certainly been a lot of work that's gone into trying to understand, well, what are the key topological properties of human brain networks and, well, brain networks more generally. And I'm just going to focus on a couple of key ones that have really received a lot of attention in the literature. So one is the idea that the brain can be subdivided into subsets of strongly connected nodes called modules. And so these are represented by the different colors here. And the idea is that the strong connectivity between nodes within a module supports some kind of common function. So this modular organization supports both specialization of function and segregation of function. Another key property is the fact that each of these modules has one or more hubs. So these are highly connected nodes, and these hubs are strongly interconnected with each other, forming what we call a rich club. That's shown in purple here. So the rich club acts almost like its own module that overlaps with these more specialized modules, and it supports integration across the network. So you can imagine if I want to send a message from this node to this node here, I need to go through this rich club of hubs to do so. And so these kind of two key facets of topological organization, modular architecture on the one hand and hubs and rich clubs on the other, thought to enable both segregation and integration of function. So widely considered to be two kind of fundamental pillars of brain organization. Also, this is, in some definitions, actually is what defines the complexity of brain function. So then it's a natural question to ask, well, how did all this complex structure emerge? And in this respect, generative models can help us out. So as I mentioned, they involve specifying a set of formal rules for constructing networks. So you can think about wiring rules or principles. We then grow these networks synthetically, and we look at their properties and we compare them to empirical data. And so if our model gives us a synthetic network that looks something like our data, we think, well, the rules that are in our model might be telling us something about how the actual data, the generative processes underlying the data, how the data have come to be. And so in a general sense, generative models have got a number of advantages. So one is that they can compress our description of networks. So rather than using any of hundreds of different graph theoretic measures for describing a network, we could potentially write down a model with just a few parameters and explain all of that complexity just in relation to variations in that small set of parameters. They allow us to make predictions about unseen data. So if we knew the values of these key parameters, we could then make inferences about what the topology of the network would look like. And in the best of scenarios, they offer insights into the generative mechanisms. Like if the model is actually telling us something about the real world, it can be informative as to the processes that actually led to the brain being the way it is. Now, there's lots of different types of generative network models in the literature. I won't go into all of those. Anyone interested, I can thoroughly recommend this review paper by Rick Betzel and Danny Bassett, where they provide a really nice introduction to the field. Today, I'll be talking predominantly, focusing mainly on this growth class of models and developmental models here, because these are the ones that have attracted the most attention in the literature. Before we jump into it, though, I just want to give a bit of a historical introduction to generative models in the network science literature more generally. Perhaps the earliest and perhaps most influential model was proposed by Paul Erdos and Alfred Renyi, and this is just a graph connected completely at random. They spent a bit of time studying the properties of these graphs and were able to derive analytic expressions, quantifying how different properties would vary as a function of things like the probability of connection in the network and the number of nodes. And this model was actually used for most of the last century to understand lots of different networks in nature. It was really only until about the late 1990s where people started to realize, well, actually, many networks found in the real world showed distinctly non-random properties. So one of those key papers was published by Barabasi and Albert in 1999. And they looked at the degree distribution of the network. So degree is just the number of edges attached to a node. And so the distribution tells us essentially how evenly distributed connectivity is across the network. And so in a random network, we'd expect a bell-shaped distribution. So most nodes have got this kind of typical average level of connectivity, and the likelihood of finding nodes with very high or low levels of connectivity is quite low. Barabasi and Albert found that a lot of real-world networks actually have a degree distribution that looks something like this. So most nodes have got low levels of connectivity, but then we've got this extended tail of highly connected nodes that act as network hubs that are much more probable than in the case on the right. So actually this degree distribution follows a power law, and they were able to pose a very simple model in which new nodes get added to the network and preferentially connected to already highly connected nodes that was able to generate a degree distribution like that. So essentially a rich get richer rule. Another key paper published in the same year was from Watson-Strogatz in Nature, where they noticed that real-world networks have got more clustered connectivity than expected for a random system. And so they started with a very regular organization here. So each node connects only to its 4 nearest neighbors. And then they randomly rewired the edges of the network one at a time until they end up with a completely random configuration. And they found that they only needed to rewire a few edges before they saw a dramatic change in the topology of the network. So we see a really big decline in the average path length of the network while clustering remains high. And so this kind of intermediate regime that they called small world appears to have the best of both worlds. It's got highly clustered connectivity, but low average path length. And we now know that it's actually very hard to find a naturally occurring network that doesn't have this small world organization. And this was certainly very attractive for the brain because in a sense, you could imagine how the clustering is related to specialization and segregation of function, and low average path length is related to integration. And then not long after that, it was shown that in many cases, the clustering is attributed to the fact that real-world networks do have this modular organization. We often see modules nested within submodules nested within modules and so on across multiple levels of hierarchy. These observations of non-random properties really gave birth to modern network science. And so a lot of these tools and techniques have been adapted to study brain networks. But the underlying generative models in these cases are quite simple and not really appropriate for the brain. So the brain doesn't start off as a lattice and then randomly rewire its connections like in a small world case, or it doesn't involve the addition of new brain regions that preferentially connect to existing hubs in the case of the rich get richer scheme. So then we can ask, well, what would be some wiring rules or principles of connectivity that might be appropriate to explain how connectome architecture has emerged? Well, we can draw some inspiration from this man here, Santiago Ramón y Cajal. He proposed perhaps what are some of the most long-standing and general principles of brain organization. He spent countless hours peering through the microscope studying the structures of neurons and concluded that all of the various conformations of the neuron and its various components are simply morphological adaptations governed by laws of conservation of time, space, and material. Now, personally, I find this to be quite a remarkable statement because he's saying that nervous systems in all of their glorious complexity can be understood just with reference to these 3 simple conservation laws. But Cajal was certainly a clever man. So if we kind of take on board what he said and think about it, we can say, okay, well, what would a network look like if it was trying to satisfy these conservation laws? If we were trying to define a network that was designed to optimally conserve material, we might end up with something like this. In this case, each node connects only to other nodes that are close, near it in space. So all the connections are short range. So we keep the overall volume of wiring of the network or its wiring cost quite low. But this does come at the expense of time. You can imagine if I want to send a message from the front of the brain to the back, I need to go through lots of intermediary connections to do so. So this isn't very efficient. We can then say, okay, well, what does a network look like if we want to conserve time? And it can be shown that a random network does a pretty good job at this, depending on how you define time. But essentially in this network, you can get from one point in the network to any other with just a few hops. But we start to see these long range connections that cut across the brain. And so this increases the overall volume of wiring in the network and therefore its wiring cost. So we're faced with a bit of a trade-off here. On the one hand, we can optimally conserve material and wiring cost at the expense of time. On the other hand, we can conserve time at the expense of material. Now, we know from a lot of different empirical studies that the brain likely occupies a position somewhere in between these two extremes. It has predominantly short-range connectivity, which serves to conserve material, but it does have a subset of strategically placed long-range connections that dramatically increase functional integration, reduce communication times, and supports globally integrated function altogether. And so this isn't, and so really it suggests that Cajal's conservation laws are in somewhat of an opposition to each other. There's a bit of a trade-off. We can conserve space and material on the one hand, time on the other, and really the job for nervous systems has been how to negotiate these trade-offs. So this is an idea that was developed quite nicely by Ed Bullmore and Olaf Sporns in their 2012 article, where they argued that nervous systems may have evolved to satisfy these competing selection criteria of trying to minimize metabolic expenditure and wiring cost on the one hand, while promoting adaptive integrated function on the other. And so the types of models I'm going to talk about today are really trying to capture this trade-off in different ways. So with that, we'll move on to model specification and fitting. So how do we specify these models and fit them to the data? So the first thing I want to emphasize is that these are stochastic models. We're defining probabilities of connecting two areas. So essentially connections are formed at random, subject to certain rules. And that then means that our results can vary from run to run. And so we're not really trying to capture the position of each and every edge in the network. We're just trying to capture the overall statistical or topological properties of the network. And I'll come back to that a little bit more later. I just want to emphasize now that, yeah, these are essentially stochastic models. And just to kind of illustrate how they behave, I'm just going to take this simple model here. This is one that has been studied, or variants of it have been studied quite a lot in the literature. So the basic idea is that the probability of connecting any two nodes, U and V, is proportional to their wiring cost, or more specifically, the distance between them. So this D here, this D parameter here, DUV, is the physical distance between two areas. You can see there's an exponential function here. So we're essentially saying that the probability of connections between two nodes, or sorry, connections are formed at random under this model, subject to the constraint that long-range connections are less likely. And that likelihood function has an exponential form. So here's an example here. We've got probability of connection on the y-axis, distance between nodes on the x. You can see this nice exponential form here. And this value, this eta parameter here, is the length scale or the distance penalty. And so higher values will incur a more severe distance penalty. So just to show that here, so we have a network. This is for a value of 0.4. As we increase the value of eta, the distance penalty becomes more severe. We're less likely to see long-range connections. Conversely, if we reduce the value of eta, we have a less severe distance penalty, and we're more likely to see long-range connections. Now, this value of eta is something that's fitted to the data. So we generate networks at lots of different values of eta, and we compare the properties of those networks to the data and find the one that's the closest fit. And again, I'll go into a little bit more detail about specifically how that's done. At this stage, though, I just want to emphasize that this is a really simple model, right? So again, we're forming connections at random, kind of like the Erdos and Renyi module, subject to the constraint that there's this distance dependence, right? So long-range connections are exponentially less likely to form. And just using this simple model, there's been a range of different studies in macaque, human, and mouse that have shown that this model is sufficient to account for lots of different brain network properties. So various types of degree distribution, spectral properties of the networks, motif spectra, distributions of clustering between us, and so on. And in a sense, it aligns with other evidence suggesting that many different aspects of neuronal organization appear to be configured in a way that optimally minimizes wiring costs. So again, under this model, long-range connections are exponentially less likely than short-range connections. So, you know, we're really unlikely to see long-range connections. So again, it's suggesting that we're keeping short-range connections quite short. most of our connections are going to be short range, and so we're in a regime where we're really close to trying to conserve material and space as much as possible. But we know that brain networks don't minimize wiring costs in an absolute sense. And we know this from some really lovely work by Marcus Kaiser and Klaus Hilgertag, performed several years ago now, where they asked if it was possible to obtain a network configuration with lower wiring cost than that actually seen in the brain by spatially permuting the positions of brain regions while keeping their connectivity intact. And they found that that is indeed the case. So here we've got the wiring cost of the macaque brain in blue and the permuted network in red. You can see there's quite a dramatic reduction in overall wiring volume. Same pattern of findings for the neuron and synapse network of C. elegans. So suggesting that it is certainly possible to find alternative configurations of brain networks associated with lower wiring cost. However, they did find that those permuted networks had longer average path length. So again, to the extent that you can think about average path length as a very rough indicator of communication times in the network, it suggests that these savings in wiring cost are coming at the expense of conservation of time in the sense of Cajal. So again, aligning with this idea that appears to be this trade-off between wiring cost minimization on the one hand and integrated adaptive function on the other. So then we can ask, okay, well, can we try to capture this trade-off a bit more directly? So returning to our simple distance-dependent model here, we've got probability of connecting two nodes exponentially related to the distance between them. In work that was first developed by Petra Vertes and Ed Bullmore, and then later extended by Rick Betzel, they included another term here, this TUV, which is a topological term designed to capture some aspect of the functional value of a connection. So under this model, again, connections are formed at random, subject to this constraint that long-range connections are exponentially less likely. However, we also have this term here that induces a bias such that if the connection between those two nodes is functionally beneficial, as quantified by some topological term, then we have this bias to form it. So we're less likely to form long-range connections, but if that connection is functionally valuable, we have a bias that tells us we might actually want to form that connection. Now, of course, the question is what is functionally valuable, and that's in the eye of the beholder. And so here you could substitute lots of different topological properties for this T term here, and these are just some of the ones that have been evaluated in the literature. The details are not so important, but the main thing is that this matching index property seems to be the consistent winner. So this property, this T term, is essentially quantifying the proportion of nodes that neighbors that two nodes have in common. So the idea is that if two nodes connect to other similar nodes, then they're more likely to form a connection to each other. So just to kind of reiterate, under this model, we form connections at random subject to two constraints. One is we're less likely to form long-range connections, but the other is that if two nodes are connected to other similar nodes, we have a bias to form a connection between those. That is an apparent trade-off with this distance penalty. So this slide here just shows model fits across these different models. This is the matching index here. So lower values indicate better fits to the data. So you can see this matching index model is doing quite well. And we have the purely spatial model that just includes the wiring cost term here in purple, the geometric. You can see it's got the worst fit to the data. So any type of trade-off appears to provide a better fit, but it's really when we're using this matching index that we get the best fit. Now, you might ask, okay, well, how exactly is that fit computed? How are we doing that? Remember that I said that what we're trying to do here is not capture the location of each and every edge or connection in the network. We're trying to capture topological properties of the network. And the reason for that can be seen just by referring back to the kind of what Strogat's findings. So they showed that you only need to rewire a few connections to see a dramatic change in the topology of the network. You see this big drop in characteristic path length. So that implies that if we were trying to reproduce every single connection in the network, we might fool ourselves. Like, let's say we were able to reproduce 98% of connections in the network. It's possible that that fraction of 2% that differs actually produces quite a large change in the topology of the networks, and the underlying system would be very different. And so this provides a rationale for focusing more broadly on statistical or topological properties of the network. And so this is what a lot of work in the field has done to date. And they do this by taking empirical data and then defining the model and simulating the model and generating a synthetic network. And then for both the data and the model, we estimate some properties. So here we've got the degree distribution in blue and the distribution of edge lengths in purple. So we get this for the data and the model. And then we convert those, distributions into empirical distribution functions, such as a cumulative distribution function, something like that. We compare the data and the model. We can do that for several different properties. So here we've got distributions for degree, edge length, betweenness, and clustering. And then we can compute the distance between these functions using something like a Kolmogorov-Smirnov statistic. And so we do that for each of these properties, and we take the maximum value across all these properties as our index of model fit. So the idea here is that model fit is determined by the property that the model reproduces most poorly. Now, recall earlier I said that we've got some free parameters that are fitted to the data. So we've got the eta parameter, which determines the length scale of the exponential penalty, of the distance penalty. And we also have this gamma parameter here, which is the topological bias, so the bias for forming functionally valuable or topologically favorable connections. And we don't know what values of those we should choose. So we essentially, for both of those parameters, we sweep a broad range of values and we just simulate the networks, fit it to the data, compute our fit index, and just repeat that many times. So we populate this kind of two-dimensional landscape, and that allows us to identify parameter regimes where our model appears to fit the data quite well. And so in this case here, darker blue is associated with better fit. And then we focus specifically on the model with the best fitting parameters. Now, I'll just say that it's important in this work to incorporate some kind of cross-validation. So ideally, you would learn the optimal parameters in a training set and then apply those to an unseen test set to obtain your final measure of model fit. This hasn't always been done in the past. This is just a scheme that we developed for Stuart's work. The details are not so important. There's lots of different cross-validation strategies out there. I just want to emphasize that if you are doing this work, it is important to think about. Cross-validation protects you against overfitting the data. It allows you to directly assess how well the model generalizes to unseen data. And also it can account for differences in model complexity. So if you're comparing models that have got different numbers of parameters, then this approach ensures that the more highly parameterized models are not overfitting the data. So that's a summary of how the models have been classically specified in the literature and how they're fitted to the data. Now I'm going to talk about some considerations that have popped up in our own forays into the field, and hopefully they'll will provide a bit of a basis for discussion both today and for anyone else who's interested in following up. So the first thing I want to talk about is the model formulation. So remember here, this is the basic form of the trade-off model, and it has this multiplicative form here where we've got this distance penalty times a topological term. Now, the key thing to keep in mind here is that these values are not actually probabilities themselves. And so then this multiplication creates a dependence between the two parameters. And it means that the values eta and gamma have got two roles. They control the relationship between the values within a term. So for example, between the values of t and gamma. And also the scaling between the terms, so the relative importance of topology versus distance. And it turns out that actually, because of the way the model is formulated, the topological term here doesn't actually exert much of an impact on connection probabilities beyond a certain distance. So here in this plot, we've shown the connection probability for a fixed value of eta, and the different lines are different values of this gamma, this topological bias. You can see that increasing the value of gamma is only affecting connection probabilities within a very small distance range. So generally connections less than 25 mils. And beyond that, all the probabilities fall onto the same line. So this really runs counter to what we would think of as should be embodied by a trade-off model, where we're assuming that the topological bias should increase the likelihood of forming long-range connections. We find that that actually isn't the case for this particular model. So to address this, we proposed an additive formulation here, where we include this additional scalar parameter here, alpha. Now this works provided that the distance and topology are on a similar scale, which we can achieve with a normalization. And in this case, this formulation allows us to separate the roles of the parameters. So alpha specifically controls the relative importance of the topological term in determining connection probabilities, and it's directly interpretable. So an alpha of 0, for example, would mean that topology has no role. And then the value of eta specifically controls the distance penalty, and gamma specifically controls some non-linear scaling of the topological term. And we compared models with and without this gamma parameter, and it turns out that it does improve model fits. So the incorporation of a non-linear scaling on topology does appear to have an important role in shaping connectivity, at least under this model. And here, when we test the performance of the model, you can see that for a fixed value of eta, different values of gamma do indeed influence connection probabilities across the full range of connection distances, as we would expect. So the model is more in line with what we would expect of an actual trade-off between cost and value, and it yields interpretable parameters such as the alpha value. And when we directly compare the fits to the data, so here we've got, for the matching index model, we've got our additive formulation with a solid black and the traditional multiplicative formulation with the dotted. You can see there's quite a significant performance advantages, or almost complete separation between the distributions here. So this additive formulation is doing much better. And as I mentioned, that the inclusion of gamma does seem to improve. If we drop gamma, we're still doing better than the multiplicative, but we do better with the gamma. So we retained it in this work. So that's the first consideration. Obviously, really thinking about how the model is specified and ensuring that it's performing in the way that we would hope that it should, or the way we intuitively feel it should. Another consideration I want to discuss is biological plausibility. So wiring cost is obviously a really important feature of these models, but all of the models to date have only quantified wiring costs based on an adult brain geometry. And we know that connections are forming, well, most connections, at least long-range connections, are generally formed before birth. And at that stage, the geometry of the brain is very different. So here we've got cortical surfaces taken from gestational week 21 all the way through to 38. You can see there's really dramatic changes in the size and shape of the brain, suggesting that the actual wiring costs that are shaping brain development when connections are actually forming are likely to be very different to those that are estimated in the adult. We just quantify that here. Here we've just got total surface area of the cortex through this prenatal period, and then the adult here, it's something like a 20-fold increase in surface area over that time. And here we've got the distribution of possible connection lengths. Again, this is the adult here. You can see that the distribution shifts to the right and has a much longer tail. So in general, when connections are actually forming in the brain, the connection distances are much shorter. And so this raises the question, well, if we accounted for these developmental differences in wiring costs, would we do a better job of fitting the data? And would we also need these topological biases, or could a simple spatial process like the exponential distance rule, would that be sufficient? So Stuart developed a way of mapping a consistent parcellation through developmental time. So we define our brain regions according to a parcellation on the adult, and then we use surface-based registration to map across onto all of these different surfaces. And this allows us to estimate how wiring costs change through early development. And then we developed two different variants of these trade-off models. We had our static model as per usual, and then a growth model where as we form connections in the model, the wiring costs are continually updated according to these developmentally specified changes in wiring costs. And when we compare the performance of the two, we find that our growth models, shown with the solid black lines, are indeed outperforming the traditional static case. So consistent with this idea that if we do account for these developmental changes in network wiring costs and geometry, then we can get a better fit to the data. Now, the other key feature of the models is this topological term over here. And so I've mentioned that generally we find that the best fit to the data is obtained when that term reflects the matching index. And loosely, we can sort of interpret this as mimicking a Hebbian-like plasticity mechanism. So the matching index is the proportion of neighbors that two nodes have in common. So you can imagine if two nodes connect to other similar nodes, then they're more likely to have similar activity and then potentially more likely to form a connection. But this is a bit of a hand-wavy explanation, right? We've got no formal model of dynamics or plasticity in there. And technically, if we're really being strict about our interpretation, the matching index would require that a node has sort of global knowledge of the network because it knows what other nodes, which nodes are connected to what. And this seems unlikely. So it raises the question, well, could we identify some simpler, perhaps more physiologically plausible rules that might help us get some of the way there, perhaps avoid relying on these kind of abstract topological rules? And really, this matching index is what's been referred to as an example of a homophilic attachment rule. So the idea that nodes that are similar to each other in some way are more likely to connect to each other. And so we were interested in saying, well, what happens if we looked at different forms of more physiologically plausible homophily? What would that look like? So we turned to data from the Allen Brain Atlas, where we extracted measures of gene expression for each brain region across 20,000 genes. So then for every pair of regions, we computed how correlated their patterns of gene expression were. And so we used this as one substitute for T. And so the idea here is that if two regions show similar patterns of gene expression, then they're more likely to form a connection. We also turned to the Big Brain Atlas. So in this particular case, we propagate lots of intermediate surfaces between the inner and outer surfaces of the cortex. And at each point, we measure the signal intensity, which in this atlas is a proxy for cellular size and density. So for every area, we have this sort of profile of depth-dependent variations in cell size and density, and then we correlate those between areas. So again, we call this microstructural profile covariance, but it's a rough proxy for cytoarchitectonic similarity, at least as defined by depth-dependent variations in cell size and density. And then finally, we did the same thing using T1, T2 rated ratio images, which has been loosely related to myeloarchitecture. So in this case, we've got three different types of, let's say, physiological homophily. one based on similarity in gene expression, one based on similarity in depth-dependent cell density and size, and the other based on similarity in depth-dependent myeloarchitecture. And we're interested in these particularly because we view them as different ways of trying to look at or test the architectonic type principle. So this is a principle that was developed by Helen Barbas and has certainly been studied a lot by Klaus Hilgertag and Alex Goulas and others. The idea is that areas with similar cytoarchitecture are more likely to form connections with each other, perhaps because they develop at similar times. And so this approach allowed us, or gave us, 3 different ways of trying to test that. Entity. Matching index model to a model that's only incorporating the coupled gene expression. The gene expression model is actually doing much better. And this is actually, this model here is just a single parameter model. So it doesn't include a wiring cost term. It only has the raw gene expression values. So essentially in this model, we are forming connections based on the strength of transcriptional coupling between regions, modulated by this gamma parameter here. It suggests that this really simple single parameter model offers a parsimonious account of the data, and that incorporating these kind of physiological constraints, or at least physiological forms of homophily, allows us to do away with these more abstract topological rules. Now, that's not to say that the idea of a cost-value trade-off in shaping brain network organization is invalid, because it is certainly possible that that is encoded in some way in the gene expression data. So for example, the raw gene expression estimates have a very strong exponential-like distance dependence, in addition to some other factors. But it does suggest that if we can actually directly measure these biological properties of the brain, we can do better than relying on these more complicated abstractions up the top. Now, the final point I want to talk about is consideration of spatial embedding. So I have talked about how we fit the data to topological distributions, but there's many different ways in which a topological distribution could be spatially embedded in the brain. So to illustrate that point here, let's consider a property like node degree. Here is a map of node degree in the empirical data. So we're essentially identifying where the hubs in the brain are. And this is what it looks like in the best fitting model. So remember, this model provides a pretty good fit to the data. So we're fitting the degree distribution quite well, but the actual way in which those distributions are spatially embedded is very different. So here in the data, it's distributed throughout the brain. In the model, it's all clustered around the center. So if we actually correlate the two, we have a correlation of nearly 0. And in fact, in this analysis, it was performed by Arina Arnautkevich-Utte a couple of years ago. We found that across 13,000 different models, different permutations, parameter values, we never saw a correlation exceeding 0.1, and the mode was actually slightly negative. So with Stuart, we looked into these physiologically constrained models, and we said, well, can we do better? So I should have pointed out that this was using one of the classical cost topology models. So if we use the physiological models, can we do better? And it turns out that we can. So here in blue, you've got the distribution of fits for the correlations for the matching index. And here is our gene expression model. You can see we are doing better, but the mode is still only at a correlation of 0.1, and we rarely get a correlation exceeding 0.3. So telling us there's more work to be done. And that's the same if we look at other properties such as clustering, betweenness, and edge length distributions. So the key point that I want to emphasize here is that it's important to not only focus on topological properties of the brain, but also spatial properties to consider how these properties are spatially embedded. And that while these physiologically constrained models certainly appear to improve our ability to explain topology and to some extent spatial topography, there's still room for improvement. And that's to be expected. You know, I think these are fundamentally quite simple models. There's a lot going on in brain development that we know occurs that aren't really captured by these models, and there's lots of different ways to take them. But I do like the idea of starting with the simplest possible approach and then gradually incorporating more and more constraints and increasing model complexity to see what different features of the data that we can account for. And so in many ways, it's a bit of an exciting area for people to get into, to start really playing around and thinking about what specific physiological constraints are either necessary or sufficient to explain different aspects of the empirical data. So to wrap up, hopefully I've convinced you that models can be quite useful for compressing the data and making out of sample predictions. And in the best cases, they can provide some mechanistic insight. And hopefully I've given some examples of how we've been able to test between competing hypotheses about the factors that might help shape connectome architecture. The ways in which models are defined and their objective functions need to be chosen carefully. And at least with reference to this specific class of models, hopefully you're convinced that we need to consider both topological and topographical or spatial properties of the networks. The results I've presented suggest that physiologically constrained models, or at least models based on some physiological form of homophily, offer a more parsimonious account than more abstract cost topology models. And at least with the data that we've found, the architectonic type principle appears to be important, but not sufficient for capturing both network topology and topography. And there are certainly other constraints that are likely to play a role. Things that people have talked about in the literature, for example, heterochronous growth, where different brain regions form connections at different times. And there's also a lot of things that we leave out of these models, such as dynamics, plasticity, overgrowth followed by pruning. And so really these are what I would see as the next steps moving forward. So I'll just close by thanking the people that did the work and collaborators, particularly Stuart Oldham, who really led a lot of this work. Thank you for all your attention.
Thank you very much.